Start recording. Okay, so today, chapter 14, homomorphisms. And I think for the first time, I have an intuition of what this is because we read about this in the category 3 book, but I already have forgotten. And there were two main probable causes of that. The first one is that it's been a while since I read that, right? And the second one is that I think this is a way more. I have a better understanding and grasp of this than the other version. They are probably the same, and it's just a skill issue on my part. But I don't know. I think I'm gonna this one's gonna stick with me more time, which is cool. Uh, Essentially, what we're gonna be talking about is what if you have a mapping which is not bijective, and when that happens, you're gonna lose some information, right? You're gonna what was the name? What was the verb that the Boolean post used? You're gonna the destroy information, right? Obliterate information or something like that.
Yeah, kinda.
Yeah. So you don't have a one-to-one mapping, and you have G and H, which are any groups. And it may happen that there is a function which transforms G into H, although this function is not bijective. For example, this modulo 6 on integers is transformed into modulo 3 in integers, and you. So how does that actually work? So you grab the values of the first, so 0 to 5 is modulo 6, and you apply to the function that maps that to modulo 3, and you're gonna get this thing, and you can represent that by tables as well. So this is the modulo 6 one, and this is the modulo 3 one, and you are essentially applying f, which is essentially to take the modulo 3 on the left to go to the right, and then you can deduplicate the columns and rows, right? Because you have two trues, two zeros, two ones, both on the columns and the rows here. So and then you're gonna have this thing. If G and H are any groups, and there is a function f that transforms G into H, we say that there is an homomorphic image of G. Um, well, the function f is called homomorphism from G to H, right?
Yes, that's a typo.
Yeah. This notion of homomorphism is one of the skeletal keys of algebra, blah blah blah. I think there is a problem. Yeah. Okay, so this is wrong, right? So the function f is a candidate of homomorphism from G to H. Because to actually be one, you have to follow this definition here, which is stricter than this thing. This notion of oh yeah, I read it right then. You had Marin.
Yeah, one way to think about it, and the conditions down there make this more explicit, is that homomorphism preserves the structure of the algebra, but it may simplify it. Like, it may
Yeah,
collapse together
yeah,
some elements, but the
yeah,
overall structure is
yeah.
preserved.
So like, I don't know. In my mind, if you have like a shape, you may have the same shape but just simpler. Like I don't know. It's kind of hard to put into words. I think the word there's gonna be a square example, right? But the square example is about rotation, which sucks to explain this. Anyway, so let's examine carefully what we mean by saying that f transforms g into h. To begin with, f must be a function from g to h, onto h. But also, f must transform the table of g into the table of h. To accomplish this, f must have the following property for any two elements, a, b, in g. So we say that if you apply f to a, which is in g, you get a prime, and f to b, and b being in g, you have b prime. Then, if you're gonna map the 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 application of the operation of the group, right, to their respective outcomes as well. So this is kind of what Marinho meant by saying that the algebra is going to be preserved, but in more concrete terms, I would say that the operation is preserved because the operation has is tied to a particular operation, as we know. So the way that I like to see it, one way to express that is by saying the algebra. I like to say that the operation is kept intact. So if you have that, and then you have that, then you have this, and then if that is true, then F is a homomorphism from G to H. So that's a very important, right? Because I'm very sure that in the exercises there will be an example that it's gonna smell like an homomorphism, it's gonna taste like a homomorphism, but it isn't because this is not gonna hold, and then you're gonna be sad about that. If there exists an homomorphism from G to H, we say that H is an homomorphic image of G. Groups have a very important and privileged relationship with their homomorphic images, as we're gonna see right now. So then we have the odd and even example, right? So what happens if you do addition on odd numbers and even numbers? What do you get? You get this thing, this table here. And then we're gonna use f from going from integers to p. And p is this universe here, and integers are integers. So we're gonna carry every even integer to e and every odd integer to o, and that's gonna be an homomorphism. We have to check that, of course. So this is easy to check because in this case we can enumerate the cases. We have four different ones. So we have R and S, and then we have the case where both of them are even, both of them are odd, or they are mixed, and then in this case even, odd, odd, even. So for example, if they are both odd, their sum is even. So if f of r is 0, this is also wrong. This is e. And f of s is o. What happens? Well, you have to check what happens with their sum, right? So we know that if both of them are odd, right, according to the table, the result is going to be even. And we have to check what happens with the sum when applying f to it, and that's going to hold, right? So this is true. And then since this is also true, yeah, actually I did that the other way around. So this is the beginning. This is what happens in G. And this is what happens in P. Well, not G, integers. And then this is what happens in P. Then so this is true, which means that this is F is an homomorphism. Yeah, so you can do the same for the other cases. That's fine. It follows that P is an homomorphic image of integers. Now, what do P and Z have in common? This is very important, right? Because we are removing information but preserving something important. P is much smaller group than integers. Therefore, it's not surprising that very few properties of the integers are to be found in P. Nevertheless, one aspect of the structure of integers is retained absolutely intact, which is the structure of odd and even numbers. Um, in other words, as we pass from integers to P, we deliberately lose every aspect of the integers except their parity. Their parity alone is retained. Um, you know what this kind of reminded me of? Now that I read this again, this reminded me of band filters. It's like high pass and low pass, because that's kind of what we are preserving from the signal, right?
Hmm.
Hmm, interesting. Another example will make this point clear. Remember that D4 is a group of the symmetries of the square, so we've seen this before. Um, every symmetry of the square either interchanges the two diagonals here labeled 1 and 2, or leaves them as they were. In other words, every symmetry of the square brings out about one of the permutations. Yeah, so we are looking at their diagonals, well, at their corners, I guess. These diagonals here. So you can either have this or that. So there is a mapping that can happen between D4 and S2. And that's exactly what's being written here. Right, so indeed, it is clear on geometrical grounds that when we perform the motion Ri followed by the motion Rj on the square, we are at the same time carrying out the motions the applied f versions of that. Yeah, and this is supposed to be an S. What is happening? This chapter is very like broken.
Yeah, there are quite a few typos in this particular section of the book.
That's weird. It follows that S2 is homomorphic image of D4. Now S2 is a smaller group than D4, and therefore very few of the features of D4 are to be found in S2. But one of them is the diagonal motions. Thus, as we pass from D4 to S2, we deliberately lose every aspect of plane motions except the motions of the diagonals. And then finally, well, as a final example, we have the coding binary code stuff, and we're going to make a function which is going to be an homomorphism by dropping the last two digits because those are just checksums, so they're not really content at all. They're just there to do the checksum stuff. Um, it is easy to verify that f is an homomorphism since b5, which is the version without the two digits, is an homomorphic image of b7. As we pass from one to the other, the message component of words in b7 is exactly preserved, while the error check is deliberately lost.
Yeah, this is basically a bit shift, right?
Yeah, this is a shift to the right. Yeah. These examples illustrate the idea inherent in the concept of a homomorphic image. The cases which arise in practice are not always so clear-cut as these, which is probably like most of them, I would guess. Um, but the underlying idea is the same. In an homomorphic image of G, some aspect of G is isolated and faithfully preserved while all else is deliberately lost. Yeah, this really reminds me of a filter now that I think about it. Theorems. Uh, um, Let G and H be groups and F. Yeah, I do have a question on this one, I think. On one of these theorems, I think I have a question. We have F as an homomorphism. Then F of the neutral element is equal to neutral. Yeah, but this is very bad in notation, right? This should have been just used different letters or like so what's it called? Um,
Think of it as a type class, Lemus.
this is not
The
programming though.
the E is polymorphic. It has different types on each side.
Yeah, but they could have done the thing that I'm not sure. Do you know this like -1 up here? What is the name of that? But down there, down here.
Subscript.
Yeah, they could have used that. Like, what are we doing? Because now they have the need of saying this thing. But yes, if you're thinking in programming terms, type classes suffice. And then you also have that the f of the inverse of A is equal to the inverse of the application of f for every element A in G. So disclaimer, in the first equation, the letter E on the left refers to the neutral element in G, whereas the letter E on the right refers to the neutral element in H. Because at first you were kind of lost on what this means, right? So you need to read this thing. So to prove the first, we know that in any group, if you have uh, yeah, I think this was the exercise that we did that took me a while to understand. That if you have two things that is equal to the same thing, by the theorem, we can just say that y is equal to neutral, like identity. Now, um, if we have this thing and we know that f is an homomorphism, then that means that we can do this, which means that this is equal to this, and hence this is equal to that. So my question, I would say, is the following. I don't understand why this is the final step of the process, really. Like, I understood this portion of it, this, and this, but how are we making the bridge here to conclude that this is the case? Does anybody know?
Uh, let's see.
Ah, okay, no, I see. You have to look at this and then at this. because then it fits this pattern matching here, and then yeah, and then it follows that the element is going to be equal to E. Yeah, mechanically I understand that. Okay, is that fine, money? Is that how you
Yeah, no,
understand
that's
it?
fine. Yeah, no, that's fine. That's totally fine.
Yeah. Okay, so next to prove true, we have this thing. We know that F is a homomorphism, so we can do this first jump, which is going to be equal to that, and that's going to be equal to that. But we from the first we know that this is equal to this, so we know that that is equal to this, right? Because we derived this out of that. It follows by theorem 2 of chapter 4 that A inverse is the inverse of f of A, that is, boom. Yeah, I don't remember. I think this is the one that says that if you have something and something else, and they are equal to the identity, then you can say this thing. I remember. I remember. Oh yeah, this is the one that I wanted to ask about, the conjugate stuff. Before going on with our study of homomorphism, we must be introduced to an important new concept. If A is an element of a group G, a conjugate of alpha is any element of this form. This should not be alpha, right? This should be A, I think. Or this should be alpha. I don't know.
Yeah, I think it should be A because it's instantiating the example to a case where you're using Greek letters, but the text is just using like the normal alphabet throughout. So yeah, it's they got it mixed up in the text for some reason.
On the physical book, it is an A, actually.
Yeah, I read in the physical book, but I don't have it open right now. Anyway, so my question is, how do we know the conjugates of A in S3? How do we know are those are the cases?
The conjugates are just the element sandwiched between every other element of the set.
S3 is all the permutations of with three elements, right?
Yes.
What are beta, gamma, like what are the elements in this case? The permutations themselves?
Yeah, they are just abstract names for the permutations.
Okay. And we have four of them.
We actually have three. You have gamma, kappa, and alpha itself.
What happened to beta?
You can't reach beta by conjugating alpha, actually. The conjugates are the right side, not the left. Or rather, alpha conjugated by beta is equal to gamma, so like the conjugates of alpha are the results that you get when conjugating alpha.
Ah, okay. So you have on S3 gamma, kappa, and alpha, and then you are deriving these other folks on the left by using the conjugate formula.
Uh,
Is that
S3
it?
has 6 elements actually, not 3.
Oh, okay.
Like
So the
it's the permutations of a set of 3 elements, so there are 6 permutations.
so they are
S3 has
six.
6 elements, yes.
Okay, so let's count. One, two, three, 4, 5. That's it.
And
There
there's
is.
identity.
Oh, and there's identity. There we go. Okay, so I was pretty
But
lost on that.
S3 has 6 elements, but note that alpha in S3 only has 3 conjugates. That is what I was trying to say. Because you can only get the 3 elements by conjugating alpha.
Okay.
That relates to an exercise we did on the previous chapter about conjugation groups, I believe.
Yeah, I already don't have recollection of that exercise, but I believe you.
It's about the relationship between the orders of the base group and the conjugations of the subgroup, right?
I don't recall. Tevo is the one
Because
that's
3 is the
pushing.
divisor of 6 in this case, right?
There was something like that. I have very like murky, blurry memory of that. But yes, I remember something along those lines.
I
As well
believe
as
it's that exercise, yes.
A itself, which may be written in two ways, right? So that and that. In H, if H is any subset of a group G, we say that H is closed with respect to conjugates if every conjugate of every element of H is in H. Is closed with respect to conjugates if every conjugate of every element of H is in H. Okay. And then another definition, let H be a subgroup of a group G. H is called a normal subgroup of G if it is closed with respect to conjugates. Okay, so this this other nomenclature is worse because you can just say normal subgroup. Am I right on that or am I wrong?
Well, it is introducing this nomenclature right now, so
No, okay. No, this is broader because this is not restricting H to be a subgroup. It is only talking about the closed with respect to conjugates. But this one is putting two restrictions on it. It needs to be a subgroup and it needs to be closed with respect to conjugates.
yes.
Okay, so this is stronger. Note that according to this definition, a normal subgroup of G is any non-empty subset of G which is close with respect to products, inverses, and conjugates. So I think this is because of the subgroup portion, and this is the new stuff, right?
Yes.
Okay, cool. Homomorphism. So we have F as an homomorphism. The kernel of F. Okay, okay. What a name. Uh, the kernel of F is the set K of all the elements of G which are carried by F onto the neutral element of H. So when you are destroying information, all the elements that culminate into into neutral, they form a set which you're gonna call the kernel. Okay, and then we have theorem 2. The kernel of F is a normal subgroup of G, and the range of F is a subgroup of H. Yeah, I think this is also one that I have questions. I think. That's cool. So let K denote the kernel of F. Good so far. If A and B are in K, this means that this is true, which it does, right, by definition. Thus, F is an homomorphism, so we also know that this is true, right? So F of AB is equal to F of A and F of B. And because of the former, we know that this is equal to AE, which is equal to E, which means that AB is inside of the capital K. This is also a typo. So good so far. Like even a monkey like myself can follow that. So now we go to another premise. If A is in K, then we know that F of A equals to E. Again, this should be capital K. Uh, thus, because of the theorem from before, if we grab the f of the inverse of A, we're going to get this thing, which is going to be equal to that, which is going to be equal to that, which means that the inverse of A is also in K. Good so far as well. Finally, A minus, this is not a minus.
It should be
The,
a
yes,
A
yeah, this
is
is
in
wrong.
K.
It should be A's in K, as Tevo
yeah,
said.
A is in K and X is in G. Yeah, this is the real deal. So then, if we do the sandwich, and we know that F is an homomorphism, then we can destructure this thing into this thing. Apply the first theorem into the last part, which is going to be equal to that, right? And then I got lost.
That's because it skipped a step. F of A is identity by definition. because A is in K.
Okay, so that means by the theorem, yeah, you have this identity and then this again, well, the inverse of the former, that's equal to E, which shows that the conjugate is also in K. Thus, K is a normal subgroup. Yeah, thank you, Marin. Thank you, thank you, thank you. Now we must prove part 2, which is to say about the range, which I forgot what it is, but I think it's going to mention here. If f of A and f of B are in the range of f, then their product, blah blah blah, is also in the range of f. Can somebody remind me what the heck is the range of a function?
Uh, the range is all of the possible outputs of the function.
So it's the size of the image.
It's the part of the image where the function actually produces an output. Like for instance, if you have a function from A to B, but every element in A goes to the same element in B, the range is the set with just that one element, actually, not the entire image.
Okay, that is correct. Yeah, yeah,
Like it's basically the smallest set that still covers all of the outputs of F.
yeah. Okay. If f, wait, let's read that. So if f of A and f of B are in the range of f, then the product is also in the range. Well, yes, because we know that this must be defined in f. Uh, if f of A is in the range of f, its inverse, which is this, is also in the range of f. Thus, the range of f is a subgroup of H. Wait, there was a jump there. How can you say that the range of f is a subgroup of H? H is the homomorphic image. But how can you make the relationship of subgroup using the range? Isn't the range H? Why isn't the range H? Am I crazy?
Well, age is a subgroup of age, so that would
Well,
actually
but
cover.
that, yeah, but I understand the technicality, but if what I'm saying is correct, this is just complicating for no reason. I doubt that. Like, why is this not written the range of f is H? There must be a reason this is here, right?
It's because well, we need to preserve the structure, the algebraic structure, right? The group structure.
You must preserve the structure. Well, but H is already a group by definition of the homomorphism, right? So H is a group. So there's already the structure of a group in H, right? So if you say that a range of
I
F is H, there's already a group there.
I don't think there's anything that implies that H is exactly the range of f, is there?
I don't see how H cannot be, because if H is the group that contains the elements of the of that exist after applying F, then how can you have an application of F that terminates in an element that is not in H? Then it's not a homomorphism, is it?
Oh, it's not an element that's not in age. It's an element like it could be the case that F doesn't cover all of age.
Ah, okay. So it's in the case that H is bigger than the
Yes.
target. That's why it's a subgroup. I see. So you could, in fact, have modulo 6, modulo 4, but F does just modulo 3 stuff. And then you're going to have elements hanging around in modulo 4. I see. Yeah, the range and H may not be the same. Okay, no, that does it for me. Okay, it took a lot of time. Sorry for my questions, but now we're done. Okay, so exercises. Like I said, I couldn't put effort this time into the exercises. I read the chapter. I hope I proved that. Uh, but I didn't read the exercises. So is there any exercise in A that you guys want to talk about? At least from 1 to 4, so I can flip the page.
Mm, exercise in A. Not really.
Okay. What about 5 or 6 in A still? Nothing so far?
Uh, yeah, no. This is fine. It's not that interesting though.
Yeah, it seems very mechanical. Just a matter of doing the operation. Okay, B. Any comments on B?
Uh, well, differentiable functions mentioned, I guess.
Differentiable functions mentioned, that's true. What else? Oh, there are complex numbers in here. Damn.
Yeah, I'm not a fan of that square root, but what can you do? And I think 6 is also related to complex numbers.
Ooh, because of this?
Yeah.
Yeah, that kind of like it's kind of funny that there are some notations that you can immediately tell they are related to something even though it's not written. Well, but it is talking about determinant, which may or may not go to complex numbers after that.
Yeah, I'm not that well versed in linear algebra, but I'm pretty sure there's a way to represent complex arithmetic using 2 by 2 matrices.
Um, if you asked me that question, I don't know, maybe 5 years ago, I could told you right now. I could have told you because differently than any other engineering degree, computer engineering is the only engineering bachelor's that has linear algebra in the first uh, period, either first or second. Everything else is whatever computer engineering does plus one. So if I did on the second period, every other engineering like civil engineering, mechanical engineering, electrical engineering, all of those guys did on the third period. So I suffered with these things from very early on. And at the time, I couldn't appreciate them properly because I was kind of like traumatized by how bad university was at that time. So I couldn't really enjoy, which differently than now. But yes, the answer to your question is yes. There is a way to represent complex numbers with matrices. Probably two by two, yes. Well, this is not surprising at all, right? Like operations on complex numbers being two by two matrices because you can represent complex numbers by 2 by 1 or 1 by 2 matrices anyway. So that's not really that surprising. C. Does anybody want to talk about something in C? Oh, composition mentioned.
Well, yes, composition mentioned.
Damn.
Um,
Wow, this is very cool, actually. This Wait, is composition a default homomorphism all the time?
I mean, they are functions. You can compose functions. So
Tem
the only
como,
question is
Marinho?
whether they would preserve the fact that they are homomorphisms. Um, I'm pretty sure they do in general, actually. So
Wait. So What is being preserved? Which structure is being
A
preserved?
It is basically saying that a homomorphism of a homomorphism is also homomorphic to the original group.
No, no, no.
So I
Yes,
guess
I
it's
understand that. I understand it. But I'm trying to think outside of the box here. Like so, like if you have functions and they are composing, right? So that doesn't necessarily means that that transformation is an homomorphism, right? Because you need to check if their components are homomorphisms.
Yeah, basically, like intuitively, the proof of this is probably very mechanical, but intuitively, F goes from G to H, and that's a typo in the exercise, by the way.
Oh,
Um,
okay. I was about to ask that. So you can have an auto-homomorphism. I was about to ask that.
I mean, you could. The identity function is a homomorphism, technically.
No, I guess. Anyway, you were saying?
But yeah, if you have a homomorphism from G to H, that preserves the algebraic structure. It just simplifies the actual domain, right? And if you have another homomorphism from H to K, again, that preserves the algebraic structure, but simplifies the domain even
No, no,
further.
no, 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 no. No. What you said and what Evo said, I understand that. If you compose homomorphisms, you get an homomorphism. That makes sense. I'm trying to figure out the opposite. If you know that the compositions make an homomorphism, can you say something about the components?
Hmm, I don't think so. At least nothing comes to mind.
Okay. Any other comments on C aside from composition mentioned?
8 is kind of interesting.
8. Is this a typo as well?
No, this is in fact an homomorphism from a group to itself.
Okay, so this is okay. So we have this function which is defined by the square, and we want to know if it is an homomorphism if and only if we have to prove that it is an homomorphism if and only if G is abelian. G is abelian. Um. Okay. So what do you have to do? I'm having a hard time figuring out why being abelian matters.
It matters because the function is a square function, right? Um,
Sure.
if you can't if you can't permute the elements arbitrarily and you try to do stuff with inverses, you can get screwed and actually not preserve the algebraic structure if well, actually you won't be able to, right? If the group is not abelian to begin with.
Yeah, I don't see that as a requirement. So you're saying that you need to be able to arbitrarily change the pick the permutation of the product, I guess. And how does that relate at all with the square? That's my question.
Hmm. F of x equals x squared.
Mm, mm, mm.
Uh,
And it's an if and only if, so the other way around is also true. So if G is
yeah,
abelian and you have an F like that, it's gonna be an homomorphism. Okay, I think I have an idea on why that's the case. I don't know if I'm saying bullshit, but here's my pitch. So, you know that you must go back to G, right?
Yeah.
So, my main intuition is like you you have to be able to go back to yourself after squaring it. But if you have an xyx and it's not abelian, you cannot group the x's and cannot group the y's, right? Because they may be in an order that they like I said, like interlaced xy xy, for example. You want to group the x's, so then you can apply f, and you want to group the y's, so you can apply f, and you know that their squares is in G. You know that their squares is in G. That's it. It's in my head. It is because you need to be able to compose the squares.
Compose the squares.
That's
Oh,
what I have in my
actually,
head.
oh, yeah, no, yeah, actually, I think that's close, but it's not quite it. It's because what you're saying first about XY, like if you want to actually preserve the algebraic structure, right? F of xy needs to be equal to f of x, f of y, right?
Yes, if f is to be an homomorphism.
If you apply the definition of f to both sides, this implies that xy needs to be equal to x squared y squared. And the only way to be able to do that is if you can flip the x and y in the middle.
Wait, the middle portion I think it's the key. It's the key. So could you repeat? So if you have xy and xy, and you want to apply f to that entire thing, right?
Yeah, if you have x, if you have like f of xy, it needs to be equal to f of x, f of y, right?
Yes.
If you expand, like if you actually apply the definition of f and you expand the expressions, the equation becomes xy equals x squared y squared. The only way to make that true is if you can flip the xy in the middle, so you get xxyy. But for that to be possible in general, the group needs to be abelian.
Ah, wait. I think I got it. Let me actually type that down. I think that's worthwhile typing down. Dev, did you get it?
That makes sense to me, yes.
Yeah, I think Marinho got it. Not surprisingly. Let me grab the tablet.
By the
So,
way, on your question on one, I believe that if a composition is an homomorphism, then it means that the functions being composed also are
oh, so
homomorphism
you do think you
because
can say something about the components? Damn.
I do believe yes, because you need to preserve the property that is that homomorphism is about, but I'm not sure how to formalize that.
Okay, so Marinho, you're talking about this thing, right?
Yeah.
Something like that?
Yeah, if you like forget the right hand side, just focus on the expression with the function application on xy and the two function applications, right?
Sure. So this.
Um, yeah, if you just apply the definition of f and expand the expressions on both sides of the equation,
Ah, okay. So
uh,
that means you're saying this, right?
yes. And if you
Uh,
expand the square on the left hand side, you get xy equals x squared y squared.
okay. And then you need to combine these and these. And in general, if the well, in general, no. If the group is abelian, then it's a piece of cake.
And if the group is not abelian, then that's impossible because that's a general x and y. And if the group is not abelian, then two arbitrary elements will not commute.
Yeah, yeah. What about the other way around though? You know that the group is abelian. How can you prove that F is an homomorphism?
Well, that's trivial because then you can just flip the y and the x in the middle because the group is abelian.
Ah, and then you can prove the property, which is this thing.
Yeah.
Ah, Got it. Thank you, Marinho. Yeah. Again, I may be stupid, but not that stupid. Damn. Okay, cool. Let's actually continue. So any more
Nine
exercises in C?
is nine is also kind of interesting, but not as much as 8.
So you have these functions on pairs. Okay, so this is first and this is second. Nice to meet you. It's been a while. Uh, yeah, but this pisses the shit out of me because this reminds me of tuple sections, and we don't have that in OCaml, and I hate that.
Hmm.
So yeah, we have the Cartesian product of the pairs, and it's saying that from from that to that are homomorphisms. Well, of course they are. What do you mean? What do you mean? Of course. Well, come on. Okay, that is not. I think this one, the 8 was way more interesting than 9 for sure.
6 and
Jeez.
7 are important, but they are just not interesting. They are important, but just not interesting.
6 and 7 of C.
Yeah, they are the base cases, basically.
For any group G, the function that is an homomorphism. Yeah, this is just creating the kernel, isn't it?
Well, this is creating the smallest possible, the greatest possible kernel, which gives you the smallest possible group as a
Yes.
result,
Yes.
which is the group of one element.
Exactly. This is massive destruction, right?
You
And
could
then
even say it's genocide.
so bad. For any group G, that and G are homomorphic image of G. Well, G is an homomorphic image of itself. And if you use F from 6, you get this one. So trivially true.
Yeah, those, as I said, not that interesting, but they do establish the base cases, so they are important.
Yeah, but those are very, very okay. Okay, D. Does anybody want to talk about D?
Uh, D2 is kind of interesting.
Every subgroup of an abelian group is normal. Okay, wait a moment. So
That
being
is.
normal, go Tiff, go.
Oh, I was just going to comment that that is easy to see because the conjugacy class of every element of an abelian group is itself. So every subgroup of an abelian group is going to include all of the conjugates of its elements trivially.
I'm stupid. Could you
Uh,
explain?
Go ahead, Tevo.
So from the past example, the conjugacy class of an element is the set of every conjugates of that element with the overall set, right?
Yes.
So like that's x ax minus one for every x in the set. But
Yes.
if the operation is abelian, if the group is abelian, then you can commute to x and x minus one, and then you get a for every x that you pick.
That is true.
Which means that a is the only conjugate of a. Which means that every subgroup is going to include every conjugate of its elements. Because the elements
Every
are.
conjugate will include. Could you say that once
Every
more again?
subgroup is going to include the conjugate of its elements because the conjugate of every element is only itself.
Ah, okay, no, that makes sense. That indeed makes sense. And it is trivial, and I am stupid. Everybody was right.
It's funny because it's kind of trivial, but it's still interesting.
Uh, okay, any other comments about D that you guys want to talk about? There is a name for this thing, isn't it? Like right and left stuff?
That is the right and left coset from the previous
Cosets.
chapter.
Cosets. And I forgot about those. Cosets. Oh, that is just multiplication. Yeah, no, I remember. I remember.
Yeah, that
Actually.
is a multiplied by every element of
Yeah,
a
yeah, yeah, yeah. Which
on
which
the
seems
right and on the left.
100% useless, but it isn't. Uh, okay, so any
Uh,
more?
3 is trivial if you consider Q, because the center of any group G is a billion, because the center of any group commutes with every element of the group.
What is the definition of a
Uh,
center of a group again? It's been a while since we've read
it's
that.
the set of elements that commutes with every other elements of the group, if I'm not mistaken.
And you're saying that that guy is a normal subgroup of G. Oh, of course
It
it is,
is.
because of what you said holds, which means that the center is a billion. Then using true, of course it is, right?
And then 4 is easy to see if you conjugate it, but if you conjugate it by one of the inverses of A or B and check what happens. And I also think you can prove 5 by that, but I wasn't able to.
Wait, repeat the secret sauce of 4,
You
please.
take, okay, AB is, we consider that AB is an age. That means that,
If you
let's say we can,
conjugate, well, if age is normal, right, then that means every conjugate of AB will still be in age, right?
Yes.
yes.
And if you pick the if you pick B to do the conjugation, so we put a B and a B inverse around AB,
Yes.
then the
BA.
B on the right will cancel out, so you get BA in age.
Yes, but what about the other way around?
If you pick A, you kind of get the same result. If you pick
Yeah.
A, -1.
Yeah, the argument is symmetric. You can go the other way.
Okay. So it's talking about. No, no, okay. I think I see. I think I see at least a draft of it. I'm satisfied with that. Any more comments on D, by the way? Okay.
Uh, Not from me.
E. Any comments on E? Commutator. What the heck is that? Is any product of this form, where A and B are any elements of G. If a subgroup H of G contains all the commutators of G, then H is normal. Contains all the commutators. So being normal means that you have the elements and their conjugates on yourself, right?
Yeah, being normal means
To respect the
every
conjugates, of course,
possible
again.
every possible conjugate of the larger group doesn't take you out of the subgroup.
Oh, wait. So that's just stronger than what I said. What I was thinking is that you have elements of the subgroup, and the subgroup also contains the conjugates of their or of the elements of the subgroup. But that's not true. It is the conjugates of the outer group G.
Yeah,
Is a conjugate.
basically if you pick an arbitrary element of the outer group G and you use that to make a conjugate of an element of age, then you are still in age. That's what it means for
Ah,
age to be
okay. You're
normal.
talking about the pieces of the bread. Okay, no, that makes sense. Dave?
I was going to say what Buddy you just said, actually.
Yeah. Okay, I need to remember that. And being normal means sandwiching with the outer, the inner, and keeping yourself in the inner. Okay.
Do you do you remember how many pieces of bread you've eaten in your entire life?
Yeah. What a question. Okay, but why is this true though? Why, if the subgroup H containing all the commutators, which is this shape here of G, why does that imply that H is normal? Does anybody know?
Where A and B, if a subgroup contains all the commutators of G, well, it's because if you try to take a conjugate of the commutator, um, the result will still be a commutator. It will have the same shape.
Wow, that is true. So if you sandwich with a C from G, you get another commutator because every element of H is already a commutator, which means that the output of the conjugate is also in G by definition. Yeah, very true,
In
very true.
in H, actually.
Oh, I said G, H, sorry. Okay, any other comments on E? And by the way, sorry if I'm slow today, but well, it's late.
Well, I guess it's called a commutator because if you pick the right element, you can commute from one point to another. Like in that example, if you conjugate by B, you're going to end up with B minus one in the other side. You can commute things using that, I guess.
Actually, if you conjugate with B inverse,
Yeah, B inverse, which gets B to the other side, cancels, and B
Ah,
inverse
now I
to the left.
understand what you said. It must be B inverse. Okay, okay. Cool. That's very cool. Wait, no, right? Because no, wait, that's correct. No, it must be B inverse. No, that is true. Any other comments on E before we move on?
hmm, not really, no.
Okay, cool. F. Homomorphism and the order of elements. So divisor stuff. Divisor mentioned. Number theory mentioned. Where are the primes? I'm waiting for the primes.
Oh, there's a bunch of primes in there.
Okay, so any comments on F? Man, I still think it's completely bonkers that you can say stuff about given the quantity of something. Like given the divisors of that amount of something or what is the relationship of that amount of something with the primes. That's crazy. Every time I think of that.
Uh, yeah, I don't really have anything to say. Like, a lot of this is very straightforward follow up on stuff that we've already seen um, in earlier chapters.
Yeah, this is what I'm talking about. Let P be a prime. If the range
If
of
the range
F
of F has an element
has
of
an element
disorder,
of order P, has an element though. The range is an amount. So what does it mean to say the range
no,
has
no,
an
the
element?
range the range is a set of all the possible
Ah,
results of
okay, I was
F.
counting that set, so that's a set. That's true. Of order P, then G has an element of order P. Crazy shit. Oh, this is not really about the quantity then, but this is still cool. Okay then, so let's proceed. G. Does anybody want to talk about G? Whenever a group
Ah,
G has a property, every homomorphic image of G also does. So you're saying that if you have an abelian group and you apply an homomorphism, you keep yourself abelian? That sounds very useful. That sounds incredibly useful, actually. Okay, does anybody want to talk about anything on G?
uh, not really. Those are very nice properties, but the proofs are pretty mechanical.
Yeah, but this is the first one that I would like to try. I would like to attempt to make it work in programming, though. Like that sounds so useful, no, doesn't it?
Uh, Kinda. The main thing though is that it's kind of tricky to to tell a compiler or an interpreter that something is homomorphic.
No, 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 no,
Basically,
no, no. We're not doing math programming. I'm saying like you're doing your everyday programming, and I'm putting the burden of that on you, the programmer. And I'm trying to think of something like I have a pure function, and let's just for the sake of the argument, let's say it's a binary function, and I notice that this function is going to be an homomorphism.
well, you can't really have an homomorphism that is a binary function, actually.
Of course you can, because well, sorry. I am going to take that back because I need two operations, right? I need the operation of the group and I need f, right? So I was thinking of the binary of the group and I said bullshit. So you have, yeah, so imagine that you have a group, right? So you're manipulating something, I don't know, a piece of data, and you identify that this thing is a group. Then you're going to write an f function that's going to do something similar to this. And I'm trying to think like, man, if I know these things, can my code reflect that maybe? Can I exploit
Uh,
that property?
if you have an operation which is an abelian group operation, that's not too difficult. The problem is, how do you prove that f is actually a homomorphism? Like the compiler will need to, well, either take that as an annotation by faith or verify that. How do you verify that?
Well, again, I was not talking about math programming, so
I'm I'm
I wouldn't expect the compiler to verify that at all. But I would
I'm not
expect you, the
talking.
programmer, to verify it.
I'm not talking about math programming either. I'm talking about, okay, if you want to be able to exploit that, well, either you're gonna do it by hand, in
Which
which
is what I'm talking
case,
about.
well, you no, I see.
Yeah,
I
because again,
mean,
I'm not asking the compiler to prove stuff. Although that would be cool, but I'm not asking for that.
uh,
Okay, let me try to get my point across because it's just I'm sounding like a lunatic, right? So the reason for that is because it already happened
I'm
multiple times, both with me and with myself and Marinho, that we notice that we have a situation at work, like real world getting your hands dirty programming, and we applied something that is understood as more theoretical, usually compiler related, right? So the same approach that the people in the 50s discovered how to make compilers, we apply that on like features that millions of people are using. And I wonder if this could be another example.
uh, I mean, I'm pretty sure that this would be useful if you're doing refactoring, right? Because refactoring is all about, well, in particular, right? If you're trying to make something more efficient, for example, and you want to preserve the meaning, then if you have more equalities that you can exploit, then that's better because you have more ways to
Mm,
try to optimize your code.
that's cool. That's very cool. More ways to optimize your code. Okay. H. Does anybody want to talk about H? How many are there? No, two remaining. Okay. H.
It is kind of interesting, actually.
Inner direct products. If G is any group, let H and K be normal subgroups of G, such that, oh, the only intersection between, oh wait, the K here is not kernel. Okay, never mind. So these are just two normal subgroups of G. Fine. And their only intersection is the neutral element because they must prove the following. Let H1 and H2 be any two elements of H. Cool. And K1 and K2 any two elements of K. Cool as well. And it
Yeah, there's
wants
a
us to prove that if
yeah
H1
there's
K1 equals to
there's a
H2 K true, probably,
yeah there's a typo there, missing two.
it implies that H1 must be equal to H2 and K1 must be equal to K2. And in the hint, it says that if that holds, then H2 inverse H1 must be in the intersection between H and K. And the same for the K version. Wait. Wait. So they are both normal, which means that the conjugates are there. Okay, Marinho, you can go. Why is this cool?
Uh, well, one and two are really just a build up to three and the conclusion after that. But basically, if you know that they are both normal, right?
Yes?
Then that means that you can um,
Do the sandwich between the elements of them and the elements of G and still be in them.
yes, yes.
That's what that means. And they are significantly different, as we know by this.
Yeah, that means if an element is in age, then it cannot be in K unless it's the identity element, and vice
Yes,
versa.
yes. And the conjugates by extension, I guess.
Uh, yeah, so basically, because the elements of K are not in H, but they are in G, you can use. Um, if you pick an element in H, which is a conjugate involving an element in K, you can do some tricks to commute the
You
elements,
said
basically.
some crazy stuff. So you said you pick an element of H and you use for the conjugate an element of K, right? That's what you said? Because K is
Yeah,
in
you
G,
can.
right?
K is in G, yes.
Okay. Okay, you have that sandwich. What do you do next then?
Uh, H1K1 equals HQK2 implies blah 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 that. So basically, if um,
If
hmm, yeah, actually I didn't spend much time looking at one. I spent more time looking at two and three, to be honest. But yeah, if
that's okay. We can go to true instead. No, true is saying that they commute.
yeah, two is saying that they commute.
Oh,
Yeah, I think the point one is also related to the commutator thing that we saw earlier, right? About having a subgroup which is made up of commutators, right?
no, but we
Um,
don't know that in this case. That was a given last time.
well, yes, but the thing is, they are not really commutators of. Well, they will be commutators of G because they are in subgroups of G. But for the since H and K don't intersect, like other than at the identity element,
Yeah.
and because if you can conjugate an element of K with an element of H and still be in K and vice versa,
Yes.
then it must be the case that H and K are made up of inverses of the elements in the other group.
Wait, what? That's very strong, isn't it? Because you're saying so you have the sandwich, right? So let's imagine that you okay, let me type that down because I think that's worthwhile. That's very cool. Okay, so let's say that you have an element, let's call it I don't know, G. No, not G, because that's going to confuse with this G. I don't know. Let's say that F is in H, okay? And let's say that I don't know, X is in K. You're saying this, right? This is in H, this thing. We know that, right? Because even though X is in K, from the perspective of H, this is just G, which means that this is there. Because we know that they are normal, right? So this
Yeah.
is in H. So this is in H. Agree?
Yes.
And then what you're saying is that you must get rid of this portion because then you would have an intersection of that with K.
That's not quite what I meant. What I meant is you can construct a conjugate of an element in H by using an element from K because K is contained in G, right?
Yeah.
And that must be in H because H is normal.
Also, yes.
But that implies that the elements of H they have like inverses of elements of K on their outside, kinda.
Yeah, I don't follow that. I think your intuition is getting you there, but because I don't have it, I cannot follow you there.
Like I think it is actually easier to prove that if you go the other way around. Like if you look at two first and then look at one, I think that's easier than looking at one and then two.
Okay, so True is saying that if you have HK, well, if H is in H and K is in K, then HK equals to KH, which means that they can commute. And the hint talks about commutators.
Yes.
Okay, I don't know how we're gonna plug the commutators in there, but that's okay.
Uh, okay, so
So,
basically, basically this is saying that for them to be inverses of each other, then if you build a commutator, then the whole thing must be equal to identity because identity is the only intersection between H and K, right?
sure, I can understand that, but how do okay, let me ask you a dumb question. How does this get into the picture? And what do you do with it? Where is this in? Can you know? We know that this is in G. What about being in H or K? How do you know that?
Uh, well, okay, you know that
Oh wait,
H,
this is the answer. Is because if all of this shit is equal to E, this must be in both, right?
yeah,
Ah, and if they are in both, then you know that the conjugates of one another is there. So for example, you can pick in H K for the conjugate, right? Well,
yeah.
I guess the inverse of K or something like that, right? And then what do you do with that?
Well, if you pick the inverse of K uh, as a conjugate for H,
That would
let's look.
be
Let's use the expression on the right, right? KH. If you do that, then what happens is you get the
right.
yeah. You
This
can
is gonna
cancel out
be
things basically.
yeah, but now you have these four things, right? So
Uh,
inverse of
actually,
K, H, K, inverse of H.
let's see. You picked
I
that.
picked inverse of K to do the conjugate, right? The
Yeah.
inverse is gonna be on the left, and the inverse of the inverse is gonna be on the right, but I already canceled that out.
Mm,
So you're gonna have this thing. What do you do next?
let's see. What do you do next? Uh,
Are we expected to do an equality here? Because I'm wondering how we get to this point. I think we must be doing the same, but from the perspective of k. Because this is from the perspective of h.
Yeah, I think it's actually a bit easier to just use the like to just try to prove the statement directly. So like, okay, you need to prove that hk equals
Uh,
k8, right?
if you had that, well, you erased it, but you could just
I can undo it.
transform the conjugate to the left to e, and then you'd have okay, h minus one is k, then k minus one k is e, and then you could probably do the same for e.
Wait. I didn't get it. Repeat the beginning. What do I do here?
H minus one is
Ah, this
k
is e.
because this is k because
Oh, this
that
is k.
time,
No, sorry.
yes, that
That's definitely true. This is k. And then all of this is equal to e.
yes, and I believe you can do the same for h.
No, but this is not proving this equality though. We're not deriving the equalitative. And I think that's what Marinho wants.
Uh, yeah, basically, you know that age is an element of big age, right? And you know that
Yes.
age is normal, right?
Yes.
This means that if you pick an age uh, that, or rather,
Oh, you
you
can
know,
multiply. No, let Marinho finish first.
so you know for sure that um, let me think for a second. You know for sure that um, hmm,
Math is hard, isn't it? Tev, do you want to try something else? Because again, we have to reach this point, right? That's
You
where
want to reach
we're
that
moving.
from the commutator?
Yeah, we need that exactly. We have this commutator, right? And we
You
need
can
to derive
multiply on
this.
you can multiply on the right by k and then multiply on the right by h.
Multiply on the right,
Multiply both sides by k and then multiply both sides by h.
and it's gonna flip them over.
It's going to get rid of the negatives on the left side and it's going to give you kh on the right side.
Okay, so
Not the
oh, okay,
negatives, the
yeah, that
inverses.
is kind of trivial though. Now that you said it, I think that just makes sense, right?
yeah, but then you still have to prove that the identity with the commutator actually holds, right?
No, not necessarily. Tevo proved by doing what Tevo said. We proves this one. What you want to prove, I think it's this one.
No. I mean, okay, sure. Whatever said proves the thing on the left, but then you need to establish that the thing on the right is actually true.
The commutator is equals identity.
Yeah.
Yeah.
Hadn't we done that on the thing that the lemmas erased?
No. What we proved is. Oh, actually, that is true, Marinho. Did you follow what he said?
You flip k to the other side and that's a
Yeah.
conjugation, so you get k minus 1k and then that's
Yeah.
identity.
You pick this thing. You exploit the fact that from the perspective of h, you can conjugate this with k, and then you're gonna have identity equals identity.
Or that too as well.
Marinho, did you follow that?
Identity equals identity.
Yeah. Okay. Let me repeat from the beginning. You grab this thing, um, and then Tevo, but how do you know that this is an H? We yeah, I think Marinho is trying to get that this is in there because we are kind of assuming it is there because we know it's equal to E. Do you see,
Yeah,
Tevo?
but then you have to establish that it is actually equal to E, is the thing.
Exactly. We are not proving Tevo because we are assuming that it is true already. Because if you don't assume that this is true, you cannot do the conjugate trick.
Okay, that makes sense. Well, the hint says that that is true, and we can see that that is true trivially
Oh, but
in
that's a
both
hint.
ways.
You have to imagine that you should be able to derive this yourself just by this thing, which is all Marinho is attempting. He's just saying h is in h, k is in k, this is equal to that. Yeah, I think this is hard. Like, it's cool, but I'm convinced now that it's not trivial, actually. And we're kind of running out of time. Anyway, so the conclusion on 3 is that we have thus proved the following. If H and K are normal subgroups of G, such that, well, that holds, and G is equal to, wait, what is this notation here? HK with no space in between, no operator in between, what does this mean?
Look at the
Ah,
exercise 3.
every x in G can be written as the product of this. This is a Cartesian product. Well, not Cartesian product because we are using the. Which operation is being used then? The G one?
That's the group of. It's just the group operation from G.
Okay,
Yeah.
so it is the G one. Then G is isomorphic to pairs. Well, this makes sense. Like, I don't know. To me, this just makes sense because if you can have products, you can have pairs. That's fine. You can do a one-to-one mapping of that very easily. Well, anyway. Uh, any comments about I, folks, before we close this up?
Not really.
Dave, any
Not from my
comments
side,
about
no.
I? Okay, fun. Uh, oh, this is talking more about conjugates. Okay, I'm gonna finish the recording now. We're gonna talk about chapter 15 next time, right?
Chapter 15. Quotient groups. Yeah, I took a peek at that on that already, and it's actually kind of interesting.